A warm welcome to all of you to our fourth and final mini course series. The Indian Women and Mathematics IWM has been organizing various initiatives over the years, including mini courses. Earlier this year, we hosted online mini courses by distinguished mathematicians like Professor Ramurthy, Professor Manjunath Krishnapur, and Professor Maithili Ramaswamy. Today, we are delighted to welcome Professor Tanvi Jain, a young and accomplished mathematician from ISI Delhi, who will be sharing her insight on perturbation theory of eigenvalues of matrices. Before we dwell into the main talk, I would like to briefly highlight some of IWM's key activities. We primarily organize 5 key events: the annual conference, the visitors program, regional workshop, winter school for young women, and mini courses. This year, our annual conference was held at BITS Pilani, Goa campus in July, and a regional workshop took place at the Central University of Tamil Nadu. In our visitors program, 3 eminent women mathematicians traveled to smaller cities to deliver accessible lectures promoting mathematics. This year, Professor M. Sundari from CMI, Professor Radhika Gupta from TIFR, and Professor Maria from Hellenic Open University, Greece, are traveling across India until February, delivering lectures to a wider audience. The Winter School for Young Women recently concluded at Sardar Patel University, Gujarat. Our mini courses are conducted online with the hope that it reaches broader audiences. Currently, Professor Riddhi Shah chairs IWM. The mini IWM initiative is primarily supported by National Board of Higher Mathematics. It also supported by Committee for Women in Mathematics, CWM. For more information, please visit our website. We invite you to explore more opportunities to get involved and contribute to our mission. Now I would like to invite Professor Abhay Soman to introduce Professor Tanvi Jain and chair the session. Thank you.
Okay, thank you, Archana. It is my great pleasure to introduce Professor Tanvi Jain. Professor Tanvi Jain is currently a professor at the Indian Statistical Institute, Delhi Center. She obtained her PhD from IIT Delhi. She worked on topics in topology and analysis of set-valued maps. Her current research interests lie in problems in matrix analysis related to areas such as Riemannian and symplectic geometry and quantum information theory. She has made significant contributions to her field, and you can see her numerous publications in very many prestigious journals. She is also recipient of prestigious INSA Medal for Young Scientists as well as the SERP's Woman Excellence Award. Professor Tanvi Jain is also an active participant in various IWM activities. So without further ado, I will ask Professor Tanvi Jain to start the lecture.
Yeah, thank you, Professor Abhay, and thank you, Professor Archana. I thank all the IWM organizers for their kind invitation. It's always a great pleasure to participate in IWM activities. Today, so we will start with a mini course on perturbation of eigenvalues of matrices. So this is basically, we study how the, So this is basically, we study how the eigenvalues change when we change matrices. Now, why are we talking? So this is a topic that I will be just touching upon. We will be talking of some very fundamental concept and results. And in the process, we will see very beautiful techniques that use both different areas, different elementary techniques of combinatorics, linear algebra, analysis, and topology. And now this is something that is not just important for matrices, that is finite dimensional operators, but also for infinite dimensional operators, both bounded and unbounded. But in this series of lectures, I will be only concentrating on finite dimensional operators, and that too, we will be just touching the fundamental part, the basic concept, so that we understand what are the issues and what are the solutions, the basic solutions. Now, the first question arises, okay, why to study all this? Why to study eigenvalues? So now eigenvalues just are not important quantities in operator theory, matrix theory, or mathematics, but they are ubiquitous in various different areas, ranging from vibrational analysis, quantum mechanics, control theory, and chemistry, physics. So now let's look at how these occur in various areas. So very few examples we will be looking at. So so generally the physical systems are described by differential operators, and frequencies of vibrations are eigenvalues of certain differential operators. Also, now most of the musical instruments are built based on the physical system that oscillate at certain natural frequencies. And these frequencies are imaginary parts of certain linear eigenvalues of certain linear operators, and the decay rates are the real parts of these eigenvalues. So if we plot the eigenvalues, we get a good idea of the sound of the musical instrument. Also, in quantum mechanics, ionization potentials are eigenvalues of certain Fock operators. The energy of the bound state of an electron in a hydrogen atom is associated with eigenvalues of certain angular momentum and Hamiltonian operators. And we have that, okay, also the spectral lines in the light of stars are differences of energies of eigenstates. That is, these are the differences of eigenvalues of certain linear operators. So now see, why, okay, eigenvalues are important. That we would be knowing, that we know. But why to study perturbation theory now? So it's a wide topic. A number of books have been written on this sole topic, perturbation theory for linear operators. Why exactly perturbation theory? Now, because eigenvalues are important. And many a times, it's not possible to calculate eigenvalues of the exact operator that describes a physical system. So we calculate the eigenvalues of a nearby operator. And obviously, then we'll need to see that how much we have digressed from the exact eigenvalues. So how much error we have introduced in this case. Sometimes the physical system undergoes a certain small change. So perturbation, what is perturbation? It's a change. So we are really seeing how the eigenvalues change with the change of matrices. So in that case, we also, it's become necessary to see what is the corresponding change in the eigenvalues. Sometimes we know the operators only approximately because of errors of observation, or we are not able to feed the exact operator, and thus we feed an approximation of the of the operator in our computers. So therefore, it becomes important to see how our eigenvalues have changed because of these errors of observation. Now, so what exactly we are looking for? Obviously, as I have just mentioned also, that our basic question is to see if two operators are nearby, if two matrices are close by. So then how near my corresponding eigenvalues of these two matrices will be. In a way, so now closeness, how we are describing. So when we say that two objects are close enough. So in mathematics, we are saying that, okay, if I'm given, so the concept of close comes with the concept of distance. So if can I actually mean, so here our basic focused question would be that given the distance between two matrices, can I express distance between the corresponding eigenvalues in terms of the distance between the two matrices? Now this is in quotes. So now we have not just mentioned about what is the distance between matrices or what will be the distance between eigenvalues. So we will be looking at that also. So this, we will more rigorously define the problem, and we will see what will be the issues and how will we solve them. Before starting with the exact thing, so we'll just have a very quick review of our theory. So this very quick review of basic concept and notations that we will be using. So MNC or MNR, so these are the n cross n matrices with complex or real entries. When I take matrix A, I'll always denote the ij, the entries of the matrix with the corresponding small letters with ij as a subscript. So A will have entries aij. The adjoint of A is A star, that has the ijth entry as AJI bar. A is Hermitian if A star is equal to A, skew Hermitian if A star is equal to minus A, and unitary if A star is equal to A inverse, that is A star is equal to A star A's identity, and normal if A star is equal to A star A. We can see that all normal matrices, so the eigenvalue, so Hermitian, skew Hermitian, and unitary matrices, all are normal. So are in at least in the 2 lectures, we will be focusing on only normal matrices, so as to say, and taking the special cases as Hermitian, skew Hermitian, and unitary matrices. Now, so eigenvalues. So just for, so in A is an n cross n matrix. A complex number lambda is eigenvalue of Ax is equal to lambda x for some non-zero vector x. And the set of any vector x which satisfies this equation, Ax is equal to lambda x, is called an eigenvalue of A corresponding to eigenvalue lambda. And we also know that the determinant of lambda I minus A is an n degree monic polynomial called characteristic polynomial, and eigenvalues of A are nothing but the roots of this characteristic polynomial. By fundamental theorem of algebra, we know that every matrix will have at least one complex eigenvalue. Also, in fact, every n cross n matrix will have n eigenvalues, because every n degree polynomial has n roots counting multiplicities. So correspondingly for the eigenvalues, the set of all eigenvalues is called the spectrum of A. And now here, there's a slight difference that we will be looking at. The set of all eigenvalues is the spectrum of A, that is the standard thing. And the multi-set of eigenvalues we will denote by lambda A. So what is the difference? So for example, if I have a 4 cross 4 matrix with eigenvalues 1, 1, 2, 2. So 1 with multiplicity 1 and 2 with multiplicity 2. So for example, let's say I have the characteristic polynomial is lambda minus 1 square, lambda minus 2 whole square. Then in that case, my spectrum, my sigma A will be that's the set of 2 points, 1, 2, whereas lambda A will be 1, 1, 2, 2. So lambda A is different from sigma A. It's not exactly the set. It's also different from the 4 tuple of, so when we talk of tuple, we are considering that order. But when we're talking of multi-set, we are now not focusing on the order. So 1, 1, 2, 2 is same as 1, 2, 1, 2. So here that is the difference. So now we come about the what is algebraic and geometric multiplicity. So every eigenvalue is a root of characteristic polynomial. So the multiplicity of that root in the characteristic polynomial is called the algebraic multiplicity of that eigenvalue. The set of all eigenvectors corresponding to an eigenvalue forms a subspace of Cn, and that is called an eigenspace. The dimension of the eigenspace is called the geometric multiplicity. In general, geometric multiplicity is less than or equal to algebraic multiplicity. And this is equal. So this is an important part that one we will actually be using implicitly, that if A is normal, then geometric multiplicity is equal to algebraic multiplicity. And so now, so as we turn to normal matrices, The fundamental theorem, again, that we have in linear algebra is a spectral theorem that tells me that every n cross n normal matrix so for every n cross n normal matrix, there exists a unitary matrix such that A is equal to U D U star. A can be diagonalized by a unitary matrix. So D is the diagonal matrix whose diagonal entries are the eigenvalues of A. And we know that D is unique up to permutation of those eigenvalues of its diagonal entries. In other words, we can also state spectral theorem as that for every n cross n normal matrix, there exists an orthonormal basis consisting of eigenvectors of A. So orthonormal basis, so that it's introduced in the basic linear algebra. So now what happens, what special happens when I have A to be Hermitian, skew Hermitian, or unitary? So now the diagonal matrix will have some special properties because the eigenvalues of Hermitian matrices are always real, of skew Hermitian matrices are purely imaginary, and of unitary matrices have modulus 1. So now correspondingly, the diagonal entries, the diagonal matrix will have that property, those properties. So just to have this complete thing. So now what is the inner product that we'll be taking throughout this course on CM? So that is the usual Euclidean inner product. So x and y are vectors in Cn. So that is summation xj bar yj. Here one should note that we are following the usual convention of matrix theory and physics that our inner product is conjugate linear in the first coordinate and linear in the second. So this is a slight so in generally in functional analysis, we take the other way around. So one should note that here. And also, so the norm corresponding to this Euclidean norm, so Euclidean norm, that is summation. So norm x, we'll use it many a times. So norm x will always denote the Euclidean norm on Cn, and that is summation xj mod xj bar, xj bar square whole square root. So we know that what is an orthonormal base. So two vectors x and y are orthogonal if x comma y is 0, the inner product between them is 0. And what is an orthonormal basis? Is a basis in which all vectors are unit vectors. So norm xi is equal to 1. And xi xj, the inner product between xi xj is 0 when I is not equal to j. So that we have the orthonormal basis. Now, coming to, so what was the thing? What our problem said that, okay, can we express distance between eigenvalues in terms of distance between matrices? And one way, a standard way to have distance between matrices is through their norms. What will be here we will be considering? We will be only restricting ourselves to two kinds of norms on matrices. One is the operator norm that is defined as, so norm A is equal to subprimum of norm AX. So that is a Euclidean norm. AX is again a C in Cn, where my x varies over all unit vectors in Cn. This is also same as the maximum eigenvalue of the square root of maximum of the square root of eigenvalue of A star A. When A is normal, then we have that my norm A is equal to maximum of mod lambda, where lambda varies over spectrum of A. And now in particular for Hermitian matrices. So Hermitian matrices have all eigenvalues real. So if we have the eigenvalues, we can order the eigenvalues, lambda 1 greater than equal to lambda n, and so on. So in that case, so what will be maximum of mod lambda in sigma A? That will be just maximum of either the maximum eigenvalue lambda 1 or minus of lambda n. So if lambda n is positive, non-negative, then it's lambda 1. If is lambda n negative, then it can be either of the two, lambda 1 or minus lambda n. Coming to the second type of norm that we will be talking about, this is the Frobenius norm. So this is nothing but if we view our n cross n matrix as an element of Cn square. So this is just the Euclidean norm on Cn square. So this is nothing but the square root of summation mod Aij square. Now this can also be written as square root of trace A star A. And again, if A is normal, then we have the expression in terms of the eigenvalues of A, that is the square root of summation mod lambda j square. So as we mentioned, so now through every norm on a non-linear space induces a metric over. So we get two metrics, we get two distances on the space of matrices. One is through the operator norm and the other induced by the Frobenius. So DAB, that is norm A minus B, and DFAB, norm A minus B, the Frobenius norm. Okay, so we have talked about the distance. At least one thing we are now clear about, what is the distance when we talk of distance. At least one of these two distances we will be taking on matrices. But what about eigenvalues? Now see, eigenvalues, we can view them, we can look at them as an n-tuple, we can look them as a multi-set, we can look them as a set, sigma A. So what exactly we understand by eigenvalues? So distance between the eigenvalues. If we want to capture the whole thing, we should look at it as an n-tuple. So every eigenvalue accounted for, irrespective of multiplicity. So if I have identity, I will take one as with multiplicity n times. So it will be 1, 1, 1, 1. So now here we should have, so in a way, when we are talking of eigenvalues, we will be happiest if we can view the eigenvalues as n-tuple. So in that case, we will need to have a way of ordering those eigenvalues. So we have n-tuple of eigenvalues and have some distance. So we view those eigenvalues as element of Cn, and then have a distance, have some distance induced by Cn. That will be the best thing that we can have. So now, for example, let's just take that. Okay, we just take the product metric. So that is maximum of this mod lambda j minus mu j. But obviously, in that case, I will need to have view my eigenvalues as n-tuples. Now, let's say that, okay, we have a way out. We have n-tuple. We can view them as n-tuple by some way or the other. And then I can define this distance. Then what will I expect? I will expect that, okay, if my A and B are epsilon distance apart, then my eigenvalues are at most epsilon distance apart. That will be the best thing I will expect. At least that is the easiest naive thing that I should expect. One consequence that I can see from here, okay, this is a strong thing, but one consequence I can see from here that, okay, if let's have this hypothesis that yes, we have something like this. We have all good thing, all positive, all happening very fine. We have this n-tuple, we have this, then we define this distance, we have this inequality. Then what is the consequence? One of the consequences of this is that I get n functions of eigenvalues. So n functions taking every matrix A to lambda j A, such that lambda 1 A till lambda n A are the eigenvalues of A, and these are all continuous. This is one of the consequences if I get. So this is a weaker notion that maybe I can study. So now the question that I can study is, okay, do I get such n functions of eigenvalues that are continuous? Now here we see that no, unfortunately, this is not the case. So if I just take the simple example 0, 1, Z, 0. This 2 cross 2 matrix. Just calculate the eigenvalues of this matrix. What will be the characteristic polynomial? Lambda I minus AZ. What will be that? That will be lambda square minus Z. And the eigenvalue would be lambda, so square plus minus square root of Z. My Z varies over C. So AZ. So now we know by elementary complex analysis that there is no continuous function whose square on C, whose square is Z. So at least we see now here that even the weaker notion that we have, so if for this 2 cross 2 matrices, we have two continuous functions of eigenvalues. No, we don't have such a thing. Then you say that, okay, then why are we really studying here? So it's even the continuity is not there. Then what do you expect that how can we have distance between eigenvalues and all those things? Why do we really bother about it? Now here we see that, okay, this is the most general case. This matrix AZ is not normal in general. So now here, if I restrict so now I don't go to arbitrary matrices, but I restrict my class of matrices. And there, what do we get something? There, do we get something nice? Now that is the question. And in fact, yes. Now we come to a beautiful theory. And so we restrict to the first, the simplest, almost the simplest class of matrices, called Hermitian matrices. And why we go there? So, in fact, one of the first results that was there in this context was more than a century back by Herman Weyl. And he proved that what we were expecting, in fact, for Hermitian matrices. What is the thing that we gain? Well, how do we, so why these become our first choice to handle? Because the eigenvalues of Hermitian matrices are real. Now, so when we started discussing that, okay, the distance between eigenvalues, what did I want? I wanted that I have a way of ordering the eigenvalues. So now here, as soon as my eigenvalues become real, I have at least some way of ordering them. I can arrange them in increasing order, I can arrange them in decreasing order. Now, just we follow, it's nothing special with increasing or decreasing, but we generally follow the convention. We will take the eigenvalues arranged in decreasing order. So lambda 1 A till lambda n A are eigenvalues of A. Then lambda 1 decreasing A till lambda n decreasing A. So the decreasing arrow will denotes that these are arranged in decreasing order. Now, what did Weyl prove? So he, in fact, in 1911, he proved a number of inequalities on eigenvalues in his very fundamental paper on this topic. And he proved that, so one of the very well-known and very fundamental result is the Weyl's perturbation inequality. So if A and B are Hermitian matrices, then the maximum of mod lambda j decreasing A minus lambda j decreasing B is less than or equal to norm A minus B. Now here you'll see that this result is, so it's the best result that we can expect. So here, but simultaneously, the proof is also very interesting. It's a very nice, beautiful proof. It has many proofs, but the one that is most well known is a very beautiful proof. It uses very nice elementary combinatorics, very elementary linear algebra. So now, here, so this lemma. So lemma 1, that is a very key result that will be actually making ourselves used to. So here, this will be something that we'll be using again and again. And it's a very simple elementary linear algebra. What I have I have an n cross, I have an n-dimensional space. We have Cn. So we are not going beyond Cn. So we have Cn. We have two subspaces M and N of Cn. Dimension M plus dimension N is greater than N. Then my M intersection N, if M and N are subspaces of Cn, M intersection N will be a subspace of Cn. That is, again, very elementary linear algebra. But it can be a zero space also. What it is saying, if dimension M plus dimension N is greater than N, then M intersection N will be a non-zero space. The proof is also very simple. So what basically we will prove? We will in fact prove a more basic, more the general result. So this will be just the dimension M plus N is dimension M plus dimension N minus dimension M intersection N. So now here, so I'll just give you a quick thing. It's a very elementary thing. So now from here, how do we get that result? So first let's prove this. So let dimension M intersection N be K, dimension M be L, and dimension N be P. So what I have, I know that these are all finite dimensional subspaces. M intersection N is a subspace of M and also subspace of N. So therefore, I can have I have basis for M intersection N and can extend to the basis for M and to the basis of N. So let x1 till xk be a basis of M intersection N, y1 till yk, y1 till y L minus k be independent vectors, be below subset M, z1 till z p minus k be subset of N, such that my x1 till xk, y1 till y L minus k is a basis for M, and x1 till xk, z1 till z p minus L is a basis for N. Then one can easily check that x1 till xk, y1 till y L minus k, z1 till z p minus k is a basis for M plus N. And therefore we have the thing. So it's just that simple. The first thing almost you do when you start doing linear algebra, they start getting introduced with vector spaces and bases. How do we get the our lemma 1 from here? M plus N is a subspace of Cn. So what it is telling me, if M plus N, so my dimension of M intersection N is dimension M plus dimension N minus dimension M plus N. And now dimension M plus dimension N, so what can be the dimension of M plus N? At most N. So dimension M intersection N is now greater than equal to dimension M plus dimension N minus dimension N. And if it is greater than, it is by given hypothesis, it is strictly greater than 0. Therefore, my M intersection N has dimension strictly greater than 0. And therefore, it is a non-zero subspace. Now, we come to the other lemma 2 that we will be using. Again, this is a very fundamental, a very elementary concept in matrix theory. So what we have? let's say A is a Hermitian matrix with lambda eigenvalues, lambda 1 till lambda n, so in decreasing order. So lambda 1 greater than equal to lambda 2 greater than equal to lambda n, let's say. And x is, so they, and let u1 till un be the orthonormal eigenbases of A with respect to this lambda 1 till lambda n. I take x to be spanned by u1 till uj. So I just take j to be something between 1 and n. So yeah, x to be spanned by u1 till uj and y to be spanned by uj to un. Then I have x comma ax is greater than equal to lambda j is greater than equal to y comma ay. As a corollary, I get from here, so let's see first, before seeing the proof for this, we see that now if x was spanned by the whole thing, so then what I get? My x comma x is greater than equal to lambda 1. So and in particular, if x is just u1, then x comma x is equal to lambda 1. So basically, my maximum of x comma ax is equal to lambda 1, where x varies over all unit vectors in CM, and the minimum is equal to lambda, the minimum eigenvalue of A, where my x varies over all unit vectors in CM. So this I get as a direct consequence of my lemma 2. Now we'll see how we prove lemma 2. So I will be just proving one side inequality and the other is very similar to it. So you can do it as an exercise. So now what we are looking at. So my x is spanned by u1 till uj. So that means my x is equal to summation aj I should not write aj, summation ai ui I from 1 to j, because it's spanned by u1 till uj and norm x is equal to 1. So then what does it mean? So what will be norm x? X comma x and ui's are all orthonormal. So ui comma ui is 1 and ui comma uj is 0. So this will give me that norm x square is equal to summation I from 1 to j mod ai square is equal to 1. So now what I have? So here just look at now x comma ax, this inequality, this quantity, x comma ax. So that is, what is that? That is summation ai ui I from 1 to j a of summation ai ui I from 1 to j. So this is equal to summation ai ui summation small ai a capital ui, and aui is lambda I ui. Ui are orthonormal eigenbases vectors. So aui is lambda ui. Now using the orthonormality of u1 till uj, I have this as equal to summation mod ai square lambda I. Because ui uj will get cancelled, it will become 0. Then I not equal to uk will get to 0. Then I not equal to k, and therefore we will be just left with I from 1 to j. So that what is this? Now summation mod ai square lambda I from 1 to j. So all lambda i's from I from 1 to j are greater than equal to lambda j. So this is greater than equal to summation mod ai square I from 1 to j lambda j. What is I? Because norm x square was 1. So we had summation mod ai square was 1. So this is nothing but lambda j dot 1. And therefore I have x comma ax is greater than or equal to lambda j. Similarly, we can show that y comma ay, just here what we'll be having is just instead of I from 1 to j, we will having I from j to n. And that will be the thing. So this gives our lemma 2. Now we will prove our main theorem. Here what will we do? We will not prove, we will basically prove an equivalent statement. What was our aim? Our aim was to prove that maximum, just remember, maximum of mod lambda j decreasing a minus lambda j decreasing b was less than or equal to norm a minus b. So that means for every j, I have to prove that lambda j decreasing a minus lambda j decreasing b, modulus of that is less than or equal to norm a minus b. Now, instead of proving this, what are we proving? We are proving that lambda j decreasing b plus c is less than or equal to lambda j decreasing b plus lambda 1 decreasing c. So how will we get this inequality? First, let's do that before proving this thing. So if I take, so now how do we get, I'm telling that how do we get this thing by actually proving this inequality. So if I take in this inequality lambda j b plus c less than or equal to lambda j b plus lambda 1 c, if I take c to be equal to a minus b, consider c is Hermitian then, a and b are Hermitian, so c is Hermitian. Now from this what do I get? With just c to be equal to a minus b, I get lambda j a b plus c. B plus c, what was lambda j? B plus c then becomes a. So lambda j a is less than or equal to lambda j b plus lambda 1 a minus b. So what I'm getting? So lambda j a minus lambda j b is less than or equal to lambda 1 a minus b. Yes. Now interchange the role of b, a and b. That I can do because a and b are Hermitian. I have no any bias towards any of the two matrices. So now I just interchange a and b. I will get lambda j decreasing b minus lambda j decreasing a is less than or equal to lambda 1 decreasing b minus a. What is lambda 1 decreasing? The maximum eigenvalue of b minus a. This is minus lambda n decreasing a minus b. And we have discussed that my norm of a minus b, when my a, because my a minus b is a Hermitian matrix, so norm of a minus b is greater than or equal to lambda 1 a minus b and minus lambda n a minus b. So therefore, I have the required inequality. So this will imply that my mod lambda j decreasing a minus lambda j decreasing b is less than or equal to norm a minus b. Because both of these eigenvalues, minus lambda n of a minus b and and lambda 1 of a minus b, are less than or equal to norm a minus b. So now again, if we just look at this, we will be proving lambda j b plus c is less than or equal to lambda j b plus lambda 1 c. So how do we do that? Now see, we'll be using lemma 1 and lemma 2. So let u1 till un be an orthonormal eigenbasis for a plus b plus c corresponding to eigenvalues lambda 1 decreasing b plus c till lambda n decreasing b plus c. And similarly, v1 till vn be an orthonormal eigenbasis corresponding to lambda 1 decreasing b till lambda n decreasing b. So what basically now what we will do is let M be the subspace spanned by u1 till uj. That were the eigenvectors for a, b plus c, and vn be the subspace spanned by vj till vn. So now immediately we can see we can apply lemma 1 here. M has dimension j and n has dimension n minus j plus 1. So therefore, there exists a unit vector x in M intersection n. Now, this unit vector is spanned by u1 till uj. Now we have lemma 2. And this unit vector is also spanned by vj till vn. So, by lemma 2, my lambda j decreasing b plus c is less than equal to x comma b plus cx. This is equal to xbx plus xcx. And xbx. So now see xbx. So that x is also spanned by vj till vn. Again lemma 2, the second inequality. This is less than equal to lambda j decreasing b. And now what about x comma cx? X is any unit vector. So we have corollary 3. So what was the corollary 3 telling me? Lambda 1, the maximum eigenvalue is equal to maximum of x comma ax, where x varies over all unit vectors. So this I can say that now, so the thing I can say is this is plus lambda 1 of c. And that is it. So this now I have got the thing. And so the simple just my screen is
Yeah, your screen is not visible. Yeah, you have
okay. I'll just again share it. Yeah, it's come. Yeah.
Yeah, it is visible.
So now, so what exactly? So we have proved Weil's perturbation inequality, and through that, I get if I restrict myself only to Hermitian matrices, then my eigenvalues, I can get a distance between the eigenvalues. That is mod lambda j decreasing a minus lambda j decreasing b, maximum of that. And this distance, so this is I get my lambda j as the eigenvalues. I can view them as elements of Cn. I can, so Rn in fact here. So Rn, and I have, so it's n tuple, I have a distance, and I know the inequality that my d infinity a lambda decreasing a, lambda decreasing b is less than or equal to dab. So not just I get the continuity if I restrict myself to Hermitian matrices, but even I get Lipschitz continuity. So it's a nice inequality that we have. So then the question becomes, can I extend this whole thing to something more? So now, what was the thing that was happening? For Hermitian matrices, I had the way of ordering. So can I do for other matrices also? So before that, coming to that, based on the same techniques, doing something more. So one can try, you can try these exercises. So the first exercise is very similar. So one can have that so instead of lambda n, just have the inequality reversed. So just you just play with this, the subspaces that you define. And we're using lemma 1 and lemma 2. One can see that this is my lambda j b plus c will be greater than or equal to lambda j b plus lambda n c. Doing something more, but using the same techniques. So here, so in lemma 1, we gave the condition when for two subspaces, the intersection is non-zero subspace. Now, try to extend it to three subspaces. What will be the condition if I want to take a look at M intersection N intersection K, where M and N and K are three subspaces of Cn? When this will be non-zero subspace. And if you get this condition, doing some work, you will get these two inequalities also. So I can just not restrict my C to, so eigenvalue of C to the minimum or the maximum. I can talk of the ijth, so I lambda I plus j of b plus c less than or equal to lambda I j, lambda I a, lambda I b plus lambda j c. So that will need a little more work. Now, what about, so now see, if I have Hermitian matrices, I have shown. If I talk of skew Hermitian matrices, A is skew Hermitian if and only if IA is Hermitian. And A will have eigenvalue, A has eigenvalues lambda, eigenvalue lambda, then I lambda will be eigenvalue if and only if I lambda is an eigenvalue of IA. I know that mod of lambda is equal to mod of I lambda. So when I take both the matrices to be skew Hermitian, I'm not really doing anything extra. So this basically comes under the purview of Wahl's perturbation inequality. Now, a little different question would be, what happens if I take one matrix to be Hermitian and one matrix to be skew Hermitian? Then what happens? So here also, it's a result by Sundar that tells me that yes, here also I can have an ordering. Now, this is a slightly a different way of ordering. Well, when you see the proof, you will realize why we are having this ordering. So now I take A to be Hermitian matrix, B to be a skew Hermitian matrix, and I take eigenvalues. So A will have all eigenvalues real, B will have all eigenvalues purely imaginary. So alpha 1 till alpha n are eigenvalues of A, I beta 1 till I beta n are eigenvalues of B, and I order them. I assume that they are ordered such that the absolute values for eigenvalues of A are in decreasing order, and for B, the absolute values are in increasing order. It's a reverse order. There is nothing special with that A always will decreasing or increasing. I can reverse the thing. Main thing is both the way we are ordering should be opposite. One we are ordering in increasing, so one then the other will have to order in the decreasing order. Then similar result we have for these two pair of matrices also. So the mod of the maximum of mod alpha j minus I beta j is less than or equal to norm A minus B. Recall again, here we will be again using, so let's call this as two subspace dimension theorem. So again, they will use the same fact. Plus, we will use the well-known parallelogram law for Euclidean. So what we have for Euclidean norms. So norm x plus y whole square plus norm x minus y whole square is equal to 2 times norm x square plus y square. That we will be using here, in fact. So what do we do here? Again, we are using lemma 1. So what we will do? We will take, so M be the subspace. So what we have to prove? Maximum, so I have to prove for any j. Lambda, so we take 1 less than equal to j less than equal to n. So for any j, I have to prove that mod alpha j minus I beta j is less than equal to norm a minus b. So here what I do is, so let M be the subspace. Spanned by the eigenvectors, the eigenvectors corresponding to alpha 1 till alpha, the corresponding to the eigenvalues alpha 1 till alpha j, and n be the subspace spanned by the eigenvectors corresponding to eigenvalues I beta j till I beta n. Then what I have? So M intersection n would be again non-zero subspace. So there exists a unit vector x belong to M intersection n. This unit vector, so let's now see here. So what about, so here if we look at norm ax square. So let's just assume that my x is spanned by alpha 1 till alpha, so the eigenvectors of alpha 1 till alpha j. So now these are spanned by the vectors u1 till uj. Let's have. So my x is summation ai ui, again the same kind of thing, 1 from j. And because my x is unit vector, summation mod ai square is equal to 1. That I also have. Now, what will be norm ax square? Ax comma ax. What is that? Let's calculate here. So that will be my ui's are orthonormal. I'm taking the orthonormal basis. That's similar thing that we. So then in that case, ax comma ax. Earlier we were calculating x comma ax. What will be the difference here now? I will be picking up alpha i's from both the sides. So this will come to be summation mod ai square mod alpha I square. I from 1 to j. Yes. So this now becomes, so now my alpha I square is greater than mod alpha I square is greater than or equal to, here becomes the point where I'm taking mod alpha 1 greater than or equal to mod alpha 2 greater than mod alpha j. So this is greater than or equal to mod alpha j square summation mod ai square, that is 1. So this is greater than or equal to mod alpha j square. And similarly, my norm bx square will be now here. So see, my beta 1 till beta n here were in the increasing order, were not in decreasing order. So again, what I'll have? I will have that this is greater than equal to mod beta j square because of the order being reversed. So that that is the place where now you are using this, the reversal of the order. Now what I do is, so here the technique is very beautiful and it's different from what we have done in the Weiss perturbation inequality. We must note that for any matrix X, norm X is equal to norm X star. So for A minus B, this happens. So norm of A minus B is equal to norm of A minus B star. What is that? Is A star minus B star. What is A star? A star is A is Hermitian, B is skew Hermitian. So this is equal to norm A plus B. So now what I have? Norm of A minus B whole square is equal to 1 by 2 times norm A minus B whole square plus norm A plus B whole square. Now this is, so this is now norm A minus B whole square. So I know X is any unit vector. So this is greater than equal to 1 by 2 norm of A minus B X square by definition of operator norm plus norm of A plus B X square. A minus Bx. So that is Ax minus Bx. Ax, Bx are vectors in Cn. Ax plus Bx. So now comes the parallelogram law. This is equal to, so this is equal to norm of Ax square plus norm of Bx square. And we have proved that this is greater than equal to mod alpha j square plus mod beta j square. What is this? This is mod of alpha j minus I beta j square. Because alpha j and beta j are real. So now this we have proved. So norm A minus B whole square is greater than equal to mod alpha j minus I beta j square. Now the question will become, okay, these were purely imaginary, these were real, but what about unitary matrices? If I take the eigenvalues, those are all lying in the on the unit circle. I cannot, so hardly, so only plus and minus one are the possibilities where we have real eigenvalues. All, so yeah, my eigenvalues in general obviously complex. I don't have a way of ordering them. If I take the absolute values, they're all one. Again, no way to order them. So how do we order them? So that becomes, so I think it's time.
Yes. Yeah.
So maybe we can continue this. So now the question is, how will do we have anything for unitary matrices? So think about it. We will continue this discussion in our next lecture just today after a few minutes. So that basically we'll talk about unitary matrices then.